a tuning fork and the box under it are tuned to one another precisely. So the box for this 262 Hertz or C4 tuning fork has a resonance curve that's fairly narrow around the 262 Hertz frequency. That means that this is the opening from which the sound normally comes out. But it's very convenient because I can actually put a microphone inside the hole and record the output of this microphone on an oscilloscope, which I have right here. So if I hit this box and record the signal on the oscilloscope, I'm going to watch it vibrate at its natural frequency. And all being well, that frequency is going to be precisely 262 Hertz. But that's not what I want to measure. What I want to measure is the damping time of this resonance curve of this box. Let's see if I can make it happen. I'm going to go to single sweep on the oscilloscope, hit the box with a mallet, and I'm going to try it again. There we go. Let me try a second time. Even more, and I position more to the right. Perfect! Okay, so I'm gonna reposition it so I have some of the clipping at the beginning go away. And you see that the maximum amplitude is 2.6 divisions on the vertical axis. On the horizontal axis, when does the amplitude decay to 1/2 of that 2.6? When it's 1.3. Where is it 1.3? I'm going to move this cursor until it's approximately 1.3, which I'm going to say is here. And that's just shy of 2.5 divisions. You see, underneath the graph here is 10 milliseconds per division. Therefore, this is approximately 25, a little bit less, 24 milliseconds. Decay time or damping time. So after 24 milliseconds, this sound decays to 1/2 of its amplitude. After another 24 milliseconds, it decays to 1/4. After another 24 milliseconds, it will have decayed to 1/8 of the original intensity, and then 1/16 and 1/32, and so on and so forth, until it gets to 0. Now that we know that the damping time is 24 milliseconds, we can calculate that delta F, the width of the resonance curve, is 0.4 divided by 24 milliseconds, or even better, 0.024 seconds. And that gives 17 Hertz, or 1/7, which is Hertz. So if we look at the resonance curve, so we have amplitude versus frequency. The point at which the resonance curve has half the amplitude is called the full width, a half maximum, or simply delta F. And by our calculation, this delta F has to be 17 Hertz. Let's see if this is true. So because this is a 262 Hertz tuning fork, there should be 8 Hertz to the left or to the right, but it doesn't actually have to be symmetric. Let's see if in fact it turns out to be this way. So I'm showing on the oscilloscope that the amplitude is maximum at the resonance frequency of this tuning fork, of this box under the tuning fork. I have a microphone inside the box that's showing this large resonance. And the oscilloscope is picking up the signal. The frequency generator is 262. And we are actually, with this speaker, emitting a sound at 262 Hertz. So this tuning fork is resonating at its resonance maximum, the top of the resonance curve. If I go off maximum, so if I move the frequency, follow the frequency on this display, I go down, you see that the amplitude goes way down according to that curve, goes way down on the oscilloscope according to that curve, and I go up now gently back up to 262. I pass and it goes back down again. Okay, I didn't go at a particularly constant speed. Let's look at the precise resonance frequency, 262, which is where the maximum amplitude should be. It's a very finicky adjustment here. There we go. So that's the maximum, okay? And if I look at the vertical scale here, it's precisely 3 divisions on the vertical scale of the oscilloscope. So let's go back down to 1/2 on the lower end towards the low frequencies, and then to 1/2 this amplitude on the higher end. And let's see at what frequencies those occur. Okay, so I'm gonna go down to 1/2. That was too fast. Okay, that's approximately 1/2. I would say here, someplace. That's 257 hertz. So that's, in fact, only 5 hertz below the maximum resonance. That's a bit surprising, right? But remember that the resonance curve doesn't have to be symmetric, so it could be only 5 hertz below and much more above to go to 1/2. So let's go back to 262 and maximum resonance, which is there, just past it, and I keep passing it, keep passing, keep increasing the frequency until I hit 1/2 the amplitude again, which is right about again a very finicky adjustment here. That is, to a very good approximation, 1/2 the original amplitude. Therefore, and that's 274 hertz. Therefore, we have plus 12 above the curve and minus 5 below the maximum of the resonance curve. And if we zoom in on that delta F and the maximum on the curve, that's what it looks like. So the peak is at 262 hertz, the half amplitude is 5 hertz below at 257, and half amplitude 12 hertz above at 274. These are the results we just found experimentally. Thank you.